like a basic well density calculation that I do. And I'll show some other stuff along the way. But the other thing I was going to do is kind of do a little intro at the beginning, because I think this is the first R talk we've had. It's at least the first one I've seen. So I was just going to go through a little bit how to get started with R. It's not very difficult. It's very similar to Python, except Python seems to have a lot of different user interfaces that are popular with it. R, I think far and away the most popular interface is RStudio. So to get started, I think in this markdown document here, I've got a little bit on, or I just have a couple links here. So the first one is a link to where R is. I can't remember, it's called CRAN, the Comprehensive R Archive Network. That's where everything, that's where they keep the new versions of R, that's where all the packages are. And so you click this link, it'll take you there. You basically just download it, you know, whether you have Windows, Linux, or Mac. Download it, install, it's pretty simple. And RStudio is basically the same thing. And that's really all you need to do to get going. And then after that, you basically just go to your start, wherever that is, open up RStudio. Well, you know how to find a program. You open up RStudio, and it'll bring up a window like this. And this is where I do pretty much all my R programming. The nice thing about RStudio is it's one designed for R, so it's like very tightly integrated with it. It's got a lot of really cool tools in it that allow you to build packages and things. So kind of as your R skills improve, if you want to start packaging up code and things like that, it's all basically there. You just need to download a few add-ons to do it. It will also, RStudio will basically go out and find the version of R that you downloaded. So you don't have to, you can point it to different versions if you want, but it generally just works out of the box. And it comes up with a few windows. So for the most part, the ones that you'll be using are, at least that I use, are these three here. So the first one here is basically just like, if you want to save a script, you would just go to File, New File, R script. It comes up, it's basically just a text editor, and you can type code there, save it, and then if you want to run code, you can run it from there as well. And there's also a command prompt, which you can sort of think of as like a Linux or a Windows command prompt. And you can type, you know, type something there, and it'll basically run the code for you. And then the third window is this guy here, and that's where plots will show up. It's also where you can get help if you need to. You can look at the different packages you have installed. You can get the help for those different packages. So, you know, I find myself Googling things a lot of the time, but generally what you need is actually already installed with most of the packages that you get. So that's pretty much all you need to do to get started with R. It's fairly simple. So the rest of this is I'm just gonna run through some code that I've got here, talk about what it does. You know, if you guys have any questions at any time, just let me know. You know, like to keep it free flowing if possible. But so basically where we'll start is just kind of going through some of this code here. R, like Python, is you can do a lot of stuff sort of with the base version of it. There's all sorts of functions built in, but you know, the main power of it is all these packages, open source packages that people have built. SF is one of those packages, and installing a package is usually pretty easy. On CRAN, they have like a big archive of all sorts of packages, and those are pretty high quality. They go through, do a bunch of quality checks, make sure they work on like all different operating systems, and make sure that when they come out with a new version that the packages work with that new version, or they tell people to update them basically to get them working. It's not impossible to get a package on CRAN, but it's more difficult than just putting it out there on GitHub. It has to be higher quality than that. If you want to install a package from CRAN, it's pretty easy. It's just this install packages command. And if we're making a script, so we just put it in here in our script, and you can just click the line you want to run, hit Control Enter, and it's basically going to start installing the package. You can see a little progress bar there. The nice thing is a lot of these packages will depend on other packages that have been built, so it'll go out, get those automatically for you. SF is decently big, so it takes a little bit to download and install. And this is my home computer, so it's not the fastest either. But so we got our package installed. You really only need to install packages once when you update R or download R. After that, they'll be available to you, and you can load them up for any analysis just using the library command. So we can do that, and it'll basically load the package that we want to run. One of the nice things about R is that a lot of these packages you download, they've got documentation built into them. So you can just go to this Packages tab here on this little lower right-hand window, click on SF, and it'll basically show you, all the different functions that are available within that package, and you can, click through those to see, how they're used. They usually have little examples that you can copy. So it's all fairly easy to kind of get started with that stuff. The other thing you can do if you have questions is just use the question mark command. So just double question mark with the name of the package will get you to that. R has what are called vignettes. They're basically like this markdown document I have here that goes through like an elongated example of how to do something. That's what these vignettes are. And a lot of packages have those. It makes it easy to kind of figure out how to get going. And then if you wanted to do, if you wanted to look at like a specific function that you're going to use, which I do this all the time, I don't remember all the arguments to functions or what order they need to be in, stuff like that. So you just type question mark name of the function. It'll come up down here and basically just give you that function, all the different arguments, and some examples of how to use it. So that's pretty much it for getting started with R. You download RStudio, install that packages to get your packages, use library to load them. After that, it's all just kind of whatever analysis you want to do. So what I'm going to go through is just like a simple well density calculation. I do a version of this all the time. This one's pretty simplified, just to run faster and be easier to explain. But I'm going to use a data set from the COGCC, and basically they've got a shape file that has like all the well surveys. So I've got in the code here just some stuff that'll go in, download that, unzip the file, and then save it in our working directory. So we should be able to run that. We'll go out, download that thing, and it went through here. Basically this, it's all fair. These are fairly self-explanatory. It's pretty much just download file is downloading the file at this link. Unzip is unzipping the file, and unlink is just deleting. So that's just deleting the zip file, so it's a little bit cleaner. Some of these things for downloading and moving files around are kind of file or operating system specific. So I don't know. I'm on a Windows machine. I don't know if this section is going to work here on a Mac or on a Linux machine. If it doesn't, you can just go to the website here and just download it how you would download a normal file and put it in your working directory. And the working directory, you can set it to be different things if you want. It basically just defaults to either where R is or if you've opened a project, you can make a specific project, it'll go to that. But if you need to know where it is, you can just use the get wd command here and it'll show you where your working directory is. So just go in, save this thing there, unzip it. You should be good to go. So we haven't really done anything spatial so far. We've just like kind of gotten our data set together. We've gotten into R. The next steps are actually going to be doing some stuff with the SF package. And so I'll point out some SF specific stuff. Hopefully we've got some R users here, so some of this is familiar to you. But I'll try and point out some things that are maybe like SF specific and some that are more just general to R that you can do. So basically all we need to do is load our shapefile. And so that's what this wells command, or this stread command does here. Pretty much all the functions in the SF package begin with st, and then they're usually pretty self-explanatory after that. stread just reads that file, so put that in and run that guy. And it'll take a few seconds, and it pulls in that shape file into this variable called wells. And it shows us a little bit of information about it here, kind of at the bottom. And we can actually look at, if you want to look at a variable in R, you basically just need to type the name of it, and it will usually display what's in it. In this case, it's a simple features collection, which you can think of as just it's like a data frame or a data table. It just has rows and columns. And the special thing about it is it has this geometry column. And the geometry column is basically just all the coordinates that are associated with that object. In this case, it's a bunch of line strings that represent well paths. The nice thing about working with simple features, or at least the thing that I like, is the data that you're working with is really just a table. I mean, you've got columns for API number here, operator, well name. You can add columns, you can filter just like you can with a normal data frame or data table. But you can have a multi-point geometry just in one column, in one row. So you don't, like when I worked in Spotfire, kind of when I started, I would have like a survey table, and then I would link that to a well table. This allows you to basically put everything in one table, and you just have this geometry column that sort of references everything, which is pretty nice. If we want to see just the beginning of an object, we can use this head command here, and this will basically just show us like the first 5 rows of this thing. So kind of what we just did is just a different number of rows. The other thing that you've got in these simple features objects is this, I call it, I think they're technically called attributes, but they're basically like header data, for lack of a better word. And they just tell you how this geometry column is projected. So in this case, our CRS, coordinate reference system, is NAT83 UTM zone 13. And then it tells us a few other things. For the most part, all you read, this is really all you're going to kind of use out of there. But that's just telling you what it is. If you've worked with spatial data at all, you know one of the big things you need to do is if you're relating things together, what you need to have all the different objects you want to try and intersect or compare against each other. They all need to be in the same coordinate reference system. And a lot of times with shape files, they're not. Sometimes they're unprojected, sometimes they're projected, sometimes the datums are different. And the nice thing about the SF package is it makes it really easy to transform those coordinates. So if you have a bunch of lat longs and you want to get them to Colorado State Plain, all you really need to know is the EPSG number. I don't know what that means, but it's basically just a number that defines a coordinate system. And so they're all kind of standardized, and you basically just need to plug that number into this ST transform function. It'll allow you to transform your coordinates to whatever you want. So this is our coordinates were here. You can see them starting to list them out. We can use this ST transform to form our data set. It takes a little bit to get that done. But we're basically just changing this to Colorado Central. So you can see that our coordinates here are now a little different than they were, and that's just because we've got a different coordinate projection system. They all should plot up or they're all still in the same place in reality. It's just how we're telling it what the coordinates mean. So that's basically it for what a features object is. I'll start doing a little bit of work with them. Does anybody have any questions kind of before I start moving on to how to manipulate them? If not, I can just move along here. So the next thing I'm going to show is how to plot some of these things. And in this case, what I'm going to do is find the longest well in this data set, and I'm going to plot that. So to find the longest well, use this line here. And basically what this line does is it uses which.max, which basically looks at a vector of data and then finds the index of the max. So if you just had a big long vector and the fifth element was the maximum value, this would return 5. And then the other thing we're going to do is we're going to use this st-length function. I might just run this st-length function here kind of on its own so you can see what it does. Pretty much all it does is goes through our simple features collection, takes those geometries, and then just for line strings looks at how long each one is, and then looks at the next one, adds them all up, and gets you a length of that feature. So for a polygon, it would be the perimeter. For a line, it's the length of the feature, and for a point, it's not going to return anything because that doesn't make any sense. So using this st-length function just got us the length of every single one of the rows of our simple features collection. If we want to find where the longest well is, we'll just use the which.max function. It says row 1540 is where our max length well is. And so we'll save that into a variable here called longest well index, and then we're going to plot it. So one of the things, if you're not a R user, I'll go through a little bit here on just how to reference things. So kind of the base unit of things, or one of the base units of things in R, or base data types, is the data frame. And the simple features collection is very similar to a data frame. So what I'm doing here will kind of work with a data frame as well. Basically, if you want to find row and column, you just use wells. So wells here is our simple features collection, or you could think of it as a data frame. And you use these square brackets to just tell you to reference a subset of that. And it's just row and column separated by a comma. So in this case, we're looking for wells, and then the longest well index, which was 1540. So we're going to get row 1540 out of this thing. And then we only want the column called geometry. So that's what we're going to get. So we're just subsetting our simple feature here to find the longest well, and then we're just going to plot it. And it should, oh, we did run the whole thing. There we go. So that's our well. And you can see surface comes out and kicks out and then goes down. Then we could use that to plot, any well we wanted. You could put like the other thing you could do if you wanted was do like a range, which you could do with just like 1 to 10. And we could plot that. And they plot as these little dots because they're like super far apart in space and they're short compared to that, so you can barely see them. But you can subset it that way if you want. So that's a little bit about kind of how you reference things, how you subset data frames, and then how that works in terms of plotting things up for simple features. When you're plotting simple features, the main thing is you only want to plot that geometry column. It'll plot like a trellis with a crap load of other things if you don't plot just the geometry column. So the next thing I'm going to do is basically look at this well and say, how do we find the pad mates for this well? So in this case, what I would do is just use something like a buffer. And a buffer is, you can pretty much just think of it as like contours coming out from an object. So it could be a line, it could be a point, it could be a polygon. It's just gonna draw contours away from that at a specific distance that you specify. So in this case, I'm going to specify 1 mile. Our projection is in feet, so this is in feet. If you're using UTM projections are in meters, so this number would need to be meters. So you just kind of have to keep that in mind. That trips me up all the time. But so to create the buffer, we just use the st-buffer function, pretty well named, and all we're doing is limiting it so that we're just, again, using that one row that corresponds to the longest well. And then we're telling it we want to buffer out 1 mile. So we'll do that. We'll create an object called buffer. And you can see that's just a simple feature object with 1 row. In this case, it's a polygon, not a line string. And if we want to plot that, just basically plot it. The other thing here that I'm kind of introducing is this $ concept. If you want to just reference one column, like an entire column of a data frame, you can use a $ to do it. The nice thing with RStudio is it's pretty interactive, so you could do wells $, and it'll come up with all the columns that are available here. So if you just wanted the measured depth column, you could do wells $MD, and that would give you that one column that's all the MDs in your table. So we can also reference the geometry column that way to plot it. The next step then is, so I've got this buffer polygon plotted, but if we want to plot the well, we do it like this. So it's the same thing that we just did, except now we're saying add equals true, and that just allows us not to erase the plot. We're not drawing a new one, we're adding to it. And then we're changing the color to red. Oop, I run the whole thing. You can hit Control Enter as well. I always hit the run for some reason. It's just a bad habit. But yeah, so there we go. We've got our buffer, we've got our well. And the next thing I'm going to do then is use this buffer to look back at the whole well data table to find all the wells that intersected. Yeah.
This is Michael. I got a question. I'm trying to follow along. I got a little behind.
Okay.
I think you just said this, but can you explain the $ again? Because it seemed like when I did plot buffer, it did the same thing as when I did plot buffer $geometry.
So buffer, I think only, well, no, it does have multiple columns. Yeah, I don't know why it worked. Let's see.
But so the $ references a column in the table?
So this is what it normally does for me anyway.
Maybe I'm a little bit off. I don't know.
Did you get a buffer that makes any sense?
It looks the same, yeah.
Huh. It's possible you removed the columns at the beginning somehow. If this thing only had one column, you could do that. So like if the only column there was the geometry column.
Yeah, I think I grabbed buffer and I grabbed only the geometry column when I made the buffer. So that would explain why.
Okay, yeah, then that would do it.
All right, thanks.
Yeah, no problem. But yeah, if you try to plot something without just referencing the geometry, I mean, it's not a big deal. It just, if you're plotting like 1,000,000 wells or something like that, and you do that, it'll try and plot 1,000,000 wells like as many times as you have columns, and it just takes a long time. So you can hit escape to stop stuff from happening. That's like 50% effective, but sometimes it actually does stop it. So anyway, where was I? The next thing we're going to do is try to find all the wells that are within this buffer here. And we're going to use the st-intersects function for that. And this is one of the functions that I use a ton, just because it's really fast. It's not, what it does is it doesn't actually go out and compute the intersection. It just comes back and tells you if things intersect. And that turns out to be really fast to do. So I'll use this a lot if I want to do like a complex spatial function on things that are near each other, so that I don't have to compare one well to every well in the data set every time I want to do something. I'll just find the wells that are near it, and then I'll kind of do my calculations on that. But I'm just going to show how it works with one example here. So I'm going to make a variable called ints for intersections. And you just use this st-intersects function. And you just need two simple features objects. So in this case, I'm comparing the buffer to the wells. So we'll run that. And so it comes back with a list. And the list is going to be as long as the first object is. And we can tell the length of something using nrow. So we do nrow buffer. That's one row. We could do nrow wells. So there's 38,000 wells. You can use that on data frames as well. But basically what this thing will come back with is a list that's the same length as your first object. So we have buffer, so we just get this one line of a list here. And then it has elements are just the indices of the wells that intersect this buffer. And so if we wanted to plot this up, we would basically use we would just use filtering to do that. So I'll kind of show you a little bit how that works. So the first thing, we're just going to plot our buffer again. And the next one, the same thing we just did. We're just going to plot, well, actually this one I'm plotting the intersecting wells. And so how we're getting the wells that intersect is we're just using filtering. So we're taking our simple features object here, wells, and we are indexing it by the first row, basically, of that ints variable. So that's our ints variable there. It could have, you know, multiple rows if we had multiple buffers. If we do that, we just get a vector of indices. So this is the indices of all the wells that are intersecting. And so everything's referenced row column. So this is basically just what rows do I want? And then this is I only want the geometry column. And if you ran that by itself, it would just be your simple features collection of all the wells that intersect. So we filter down to that, and then I'm just sticking that in the plot function here and running it. So we get our buffer, we're plotting all our wells that intersect on top of it, and then we can plot the original well that we started with the same way we did previously. Okay, what am I doing here? So the next thing I'm going to talk about is, you know, one of the things that I've actually done a lot is I'm on the business development group, so we do a lot of counting up sticks, and I was not having fun drawing sticks by hand constantly. So I just wrote some stuff to, you know, fill in gaps with sticks so that I could kind of count them up and evaluate plays faster. And this isn't like that. I'm not going to go through it's pretty complicated to do the whole thing. I'm just going to show like how you would actually make your own feature and plot that up and add it into your simple features collection. So the first thing, basically what I'm going to do here is just figure out what are the coordinates of some sticks that would go in this spot. And I'm just going to look at the max y value. I'm going to use that as kind of my y value here. I'm going to use the min y value here. And then I'm going to use the max x value, which is like the x value of this point. So that's all I'm doing here is just calculating the coordinates of a few points along this well so that I can then add some values to them and make some sticks that are going to fill in these gaps. So that's what this stuff does. Let's see, I'm not sure if there's nothing really too exciting in here. I guess if you, this one is kind of useful. If you want to get the coordinates of a simple feature, like you just want to have a data frame of the x's and y's, you use this st coordinates function here. So right here, what I've got is I'm just filtering down to the longest well again. And in this case, I'm saying, okay, give me the coordinates of that. So if you do that, it'll give you this, comes out as a matrix with X and Y, and then it has like an ID that basically tells you what feature it belongs to. Because we've kind of taken that long or that wide data from the column, the geometry column, and now it's long, like maybe a survey file would be. So here I'm just kind of filtering through and figuring out, you know, where are the coordinates of these points so that I can use them to make some new sticks. I won't really go into that. So then the next thing I'm going to do is actually do some adding. So all I'm doing is taking the max x value, so the x value of this point, and then I'm adding 660 to it. And then I'm adding 660 to it again. So I'm just making some x coordinates for some sticks. And then here I'm making some y coordinates for some sticks. And then I am going to make like an ID column here that is gonna, because I'm making, in this case, I think, I don't know, I don't see how many sticks come out. I don't remember. We're making some number of sticks. And I'm going to put all that into a data frame, which is, like, as I've said, one of the kind of main data types that R has. And so all you do to make a data frame is just data.frame, and then these are all the things you want. You could go on forever adding stuff in here. And these are all just vectors, so just a one-dimensional object. So we can look at X. Here's X. Y is that guy, and ID is that. So if we make our data frame, just a little table, X, Y, you got one stick, you got second stick here, you got the third stick, and these are the coordinates of those endpoints. So then the next step then is how do we actually take that and like turn it into a simple feature so that we can combine it with the wells that we've already got. And this guy is a little complicated. I'll go through it kind of slowly here. Maybe best to break this. Well, you can't really break it into parts, I guess. The way to make these things into simple features is there's all sorts of different ways to do it. It depends on if it's a line string, if it's a polygon, if it's a point. The best way to find examples is if you go to the packages thing, go here, and actually do the question mark SF, and you'll get to the vignettes. And one of them is on, I don't remember which one, but one of these is on how to actually create simple features from scratch. And so there's examples of kind of how to do all the different ones. And I pretty much just pulled this straight out of there and threw my data into it. But pretty much all I'm doing here is using lapply to loop a function. And so that's probably something worth talking about here with R. R is pretty slow to do loops, and it has a lot of functions built in that are much faster and, in my opinion, more user-friendly. Coming from VBA before that, like I absolutely hated writing loops and keeping track of counters and all that stuff. Like I still do it in R sometimes, but R has a lot of functions that just let you apply one function over and over and over again in a loop. And so lapply is one of those. I think it stands for list apply, and it just means that it applies whatever function you want, and then the output comes out as a list. And so it has, it looks like there's a lot in here. There's really just kind of two arguments to this thing. It's just, what am I applying it over? And then what is the function that you want me to apply? And in this case, I'm just sort of declaring a little function in the line here that takes my data and then turns it into a line string, and then does it again, it comes out with a list of line strings. So what this thing is doing is it's applying this function here, which makes the line strings over an ID. And so that's this ID column here. And so another useful function actually that I could point out here that I use all the time is this unique function. So if we have our ID variable here, it's 112233. If we use unique, it'll just collapse that down to only unique values, so 1, 2, 3. The other thing I tend to use a lot is I'll use unique and sort all the time. So like if I want to know who are all the operators in our well data set, we could do sort unique wells operator, and it would just give us an alphabetical list of all the operators in there. So kind of an aside there. But anyway, basically what I'm doing is I'm applying this function here over all the unique values in ID. So ID is just, stick 1, stick 2, stick 3, but there's multiple rows. And so what I do is this guy here is just filtering my coordinates data frame down to whatever row happens to match the ID that I'm looking at. And that's when it loops through the function, it basically just loops through values of this, and it's whatever value you put here in your function thing. So in this case, it's looping through ID is going to be become this I variable. And so I'm just filtering down to whatever ID in my coordinates data table matches whatever ID it happens to be looping on at that point. And then this is just how you convert to a line string, which you can pretty easily look up in these SF vignettes here. So if you run that guy, makes a little group of line strings. They have not been combined into a simple features collection yet, so they're kind of out there floating on their own in a list. And so this guy will go through. You just use this stsf command, and you tell it what your geometry column is. And you can add a bunch of other stuff in here too. Like if you had a bunch of vectors that represented things like depth of the well and TBD, all that kind of stuff, you could. It works basically the same as the data frame function does. So you could add other stuff in here, whatever. I don't have a TBD column, so I can't really add that in. But it just needs to be the same length as this, so 3 values. The last thing that we need to do, so we've created our fake wells kind of in their own simple features collection now. The problem is they don't know where they are, so we have to tell it what projection they have, and use the stcrs function to do that. And it just sets the CRS value. And in this case, we're just going to set the value of our CRS, our coordinate reference system. We're going to set it the same as what our wells are, since the XY value should be the same. We'll just run that. And then we should be able to plot everything up. So I'm just sort of, the plotting I'm doing here, I'm just kind of adding one thing at a time. So this is all stuff that we did previously. And this last line here is just adding the new wells that we created. And so there we've got our 3 wells that we created. And so you can do that with, they don't have to have 2 points. They could have, as many points as you want, be any type of geometry that you want as well. It's just an example there. So the next thing I'm going to show then is how do we combine these things together. So we created these wells, but let's say we want to actually add them to our wells simple feature object. This is how we would do that. We use the rbind command. So rbind stands for row bind, and it just takes 2 data frames and puts them together on top of each other. And the only thing you have to do is make sure that they have the same number of columns. Or they have the same names of columns. It doesn't like it if you don't. So that's what we're doing here. This line here is basically just saying, take the object we created, G, which is those sticks that we created, and only take the columns that have the same names, or that are, let's see, what is this? I'm confused on what I'm even doing here. So the way that we find names of things is with the names function. So if we want to know the names of the columns in our wells, in our wells data frame, we just do names of wells. So that's what is in there. And in this case, what I'm actually doing here is creating a bunch of fake columns in our new data set that represent these other columns in our wells data frame, and I'm just giving them NA values. So right now, if we look at the wells we created, they've only got 1 column, geometry. So what I'm doing is just finding the names of the wells, simple features object that doesn't include geometry. So that's what this guy does here. It's saying the exclamation mark is like it negates something. So if you had a true, it would make it a false, false would make it a true. And all this guy's doing here is saying, here's the names of my wells. Now find all the names of my wells that are in a vector. In this case, it's just a single vector called geometry. So it's going to give us a bunch of true falses. And it's saying that this is the one called geometry. All these are not called geometry. And then we're just going to negate that. And then that's going to allow us to just choose all the columns not called geometry. And if we run that, it lets us add a bunch of blank columns to our fake data set so that we can combine it with the new one. And we'll do that here with rbind. And so now we have our fake wells kind of added to our data set. And if we do any density calculations, they'll be combined in there. But I use rbinding these things quite a bit. A lot of times I'll be taking like section shape files from like different counties or whatever, and you need them all to be in one. You do that with the rbind command, and it gets you kind of one nice table that has everything you want in it. The next thing I'm going to show then is kind of how we start clipping stuff. So that's one of the ways that I get to the density calculation is I'll just clip the wells inside the polygon. And we'll use the st intersection function for that. So the st intersects function just tells us like true, false, do these things intersect, even if it's only like 1 by 1 foot. And it doesn't change the values of them at all. It just says, do they intersect? The intersection function actually is like a cookie cutter. So it's going to take the polygon that you give it, or whatever you give it, in this case the polygon, and the lines, and it's going to clip those lines so that they are within the polygon, or that you only get the parts within the polygon. And so we'll run those guys here. So we'll run our intersection again, because we just added all these fake wells to our data set. And if we want those to be included, we'll have to run it again. So we'll hit the ints again to get our intersections. And again, that's just a list of all the values of well, or all the indexes of wells that intersect. And then the intersection here is actually going to take the intersection of them. So we're going to filter down to, you could use the whole wells data set if you want. It's just really slow because you're kind of comparing everything to everything else. If we just filter it down to things that might possibly intersect, or that do intersect, it'll make things go a lot faster, especially when you're running this over and over and over again. So this is just filtering down to the intersecting wells, and this is just the buffer that we're intersecting with. So if we run that, it'll give us, if we run this whole thing, it'll give us the segments that are actually within the polygon. The other thing it does is it comes back with this warning message, and this is sort of just like a general thing that happens with doing all these spatial calculations. What's going on is you've got a polygon and then you've got a table, and they both have their own other columns associated with them. So the buffer, you know, might have one set of columns with it, and then the wells might have an unrelated set of columns. And when you're intersecting things, it doesn't necessarily know what columns you want to go where. Or if they need to be changed. Like maybe you have a length column in your wells data set, and now you've clipped the wells. It's not going to change that well length column. So it's just sort of a reminder that like things might be changing. You might need to do some stuff here to make your numbers go around. What it does in this case is it assumes variables are spatially constant. So like if I had a buffer and I had a company name on it, like I had Ovintiv as the company name, it would propagate that company name or that column to all the things that it intersected. So just something to keep in mind. And it's the reason that when I intersected them, I only took the buffer geometry column, because I didn't want anything from the buffer to be put on the wells. So it is useful to have that being done, but you just kind of have to remember that it is being done and make sure that you're getting what you want. So if we want to plot that whole thing up again, it's just this series of expanding plot lines, and the next one here is just we're only plotting our intersecting geometries. And so that's the blue here, just getting the pieces of the wells that are in the polygon. And so this is more or less how I do some of these density calculations, you know, up to this point. Like you consider one well at a time, you draw a buffer around it, you find the wells that are near it, you clip to just the wells in the buffer, and then what I'm going to do is just sum up the length of all the wells inside this buffer and divide by the average length of the wells to get an approximate number of wells. And I do that because like you could have a bunch of little pieces of wells in here. You don't really want to count those as full wells. So we're just sort of normalizing to something like a full well density. So that's what these lines do here. This one here is just using, again, that st length function to get the length of all these little intersecting pieces. And we are setting it, we're creating a column in our well ints spatial features collection that we created here. We're just creating a new column called length. and we're setting it equal to this guy here. So we'll run that, and it'll give us our length of all the little pieces. That's this guy here. So there's some really short ones. And then what we're going to do is just sum them all up. So pretty simple function, just the sum function here. One of the things you do need to be careful of, though, is if you have NA values in something you're trying to sum, it'll throw an error. So there's this na.rm equals true, just removes the NA values. I pretty much always set that, because I almost always have NA values. Shouldn't in this case, but we'll just run that. It'll get, and this is just getting us the length of all of these little pieces of wells that are inside this polygon. And then the density I'm saying is just that length divided by the average length of all these wells. So the mean is the average function in R. So we run that and we get our density. 95, so that's a lot of wells. That is basically the density calculation that I'm going to show here. What I will do a lot of times is clean this up a little bit. So one thing I'll do is I typically just use 2-point sticks. That makes things faster, and it gets rid of like these little pieces here that you don't want to count. There's a lot of different ways to do that. The other thing that you can do is a lot of times you don't want to consider all the wells. So like if this well was drilled this year, that might, if you're trying to relate to performance, that's going to be a lot different than if this well was drilled 20 years ago and it was the first well here. So a lot of times I'll do all sorts of different filters prior to this step to kind of, maybe these wells are within the polygon, but I want to filter them out for whatever reason. And I showed how you do some filtering. I guess I can show it fairly quick. It's not too difficult. So it's just, if you want to, let's say we want to define just, well, let's just find wells from extraction oil and gas. So we would just do our wells, and we would say we only want rows where the operator column of the wells is equal to, use a double equals for comparisons in R. Extraction oil and gas. We want all columns. So that would be how you would do something like that. You could use a date, you could use a TBD filter, whatever. But you'd probably do that before you did all this summation here. So the next step then is I'm basically just going to run through, I'm going to take all the stuff that we just did and sort of combine it into one function called get density. And it just operates on one well. And what we're going to do is just loop that over all these different wells, and it's going to come back and it's going to give us density. I'm actually not going to run it now because it takes like 10 minutes or so on my computer here. One of the reasons that it takes a long time is these are full surveys. So there's like hundreds of points in each one of these guys. There's a lot of comparison being done when you do that. The other reason it takes a long time is, you're just doing a lot of comparisons in general, comparing, even if you do the intersection thing to filter things down, you're still doing a lot of comparisons, a lot of intersection calculations. The way that I typically get around that is to run this in parallel. I'm not going to go through that now, but if anybody's interested in how to do that, reach out to me. I can show you. It's not very difficult. It's one of the reasons that I tend to use lapply to loop functions, because if you can get your function in a format that can be looped with lapply, you really just need to use the par lapply command or function, and you just need to do like a couple steps before that, and it will pretty much handle everything for you. Loop your function in parallel, and however many processors you have, it can really save a ton of time. Even if you have 2 or 3, it'll speed it way up over 1. Anyway, you guys can maybe run through this one or this example on your own here. Sorry, I haven't been paying attention to the comments at all. So if you do want to interrupt, you probably just unmute yourself and speak. Basically what I'm doing here is just filtering down to only horizontals, because there actually are a bunch of verticals in this data set. And typically you only want horizontals, at least for this calculation. It's not really geared for verticals. So this will filter us down to just our horizontals. And this just filters us down to Wattenberg, so we don't get every well in Colorado. The other thing I'm doing here that's sometimes pretty useful if you're running into the things running too long is ST simplify. And this is especially useful if you're loading up like a county shape file or something like that has a ton of points, and maybe you just want to view it zoomed out and you don't really care if it has all that, all those points defined in the polygon. You can use this ST simplify function. There's not much to it. You just tell it, I want to simplify my wells simple features collection, and I want the tolerance to be 20 feet. And it'll go in and just try and remove points to get it as close as it can within 20 feet. So if you have a bunch of polygons that are like exactly abutting each other, it can screw that up. So it might be a case where you wouldn't want to use it, but in this case, like, it can help you speed up by getting, you don't need a million points along all these surveys that are more or less straight. So it just helps you get rid of some of that stuff. Then the next thing I'm doing here is just kind of what we did previously. I'm just creating a ton of buffers now. So in this case, I'm making a buffer for every well, and I'm getting the intersection of every one of those buffers with all the wells. So we'll run that. I don't think it'll take too long. Yeah, it doesn't take too long. So that is one of the nice things about SF is it's pretty fast. I mean, if you were writing loops to kind of do those comparisons yourself, first, like, how do you define those comparisons is difficult. That's all defined here. And also, this is just the code behind this is pretty optimized. So it's really pretty quick to get intersections between a lot of things. I mean, we're comparing 10,000 wells to 10,000 buffers, and just does that in a couple seconds. So it's pretty nice for things like that. The thing that we did differently here in this case is previously we were only just looking at one buffer from one well. This one tells us for each buffer which wells intersect that buffer. So you get a big long list in this case. And the next thing here is I'm just taking pretty much all the things that we did previously. I'm just turning them into a function that will get density for any well if you give it one of those buffers and then you give it a subset of wells that intersect the buffer. Because I use, I tend to not write loops, for loops and while loops. I tend to make a lot of intermediate functions and to use apply. You kind of have to, but it's pretty simple in R. It's really just, what do you want the function to be called? Equals function, and then here's all the things that go into it, and then curly brackets, and then your code, and whatever the last line is in your code, that's what's going to come out of your function. So in this case, all I'm really doing is just what we did before. So I've got my buffer, I've got my wells that intersect it. I'm actually clipping here, so using that ST intersection function. I'm also using the suppress warnings function. Because if you have something that comes out with a warning and you loop it a million times, it'll print out that warning a million times, which is annoying. So, not always the best practice, but sometimes these functions, like, they just always spit out a warning, so you have to tell it not to do that. And then I'm just doing the density calculation, so summing up the length, dividing by the mean, and that's all this function is basically doing right here. And you just declare it like this, and you get it. It's basically available for you to use. I do find a lot of times if I have a lot of packages loaded, I will sometimes come up with names of functions that already exist in packages, and it'll usually warn you like it's masking from something. If that happens to you and you, for whatever reason, really want to keep that function name, or sometimes you'll load packages that have conflicting function names, you can just use the name of the package and double colon, and that will specify like, okay, I mean this function from this package. So just maybe something to keep in mind. But in this case, we wouldn't have to do that because this is a unique function name. And then all I'm doing is using lapply to run that function again, to run that function over and over. So I'm running it for each buffer, and I'm basically just subsetting the buffers with the row of the buffer here, and then plugging that in that function over and over and over. It comes out, and then the only other trick, I guess, is I'm using this guy here to convert it to a vector from a list. That's basically it. I'm not going to run it again because it takes a long time, but this is what it looks like. So if you want to plot it, you would just use, just get the actual density column here. So we've run our function. We've got a vector called density. We're going to add that vector to our Wells simple features data frame. And then we're just going to plot that column. So in this case, you're choosing a different column. You're not just plotting geometry. If you choose a different column, it will try and figure out, like if it's a number, it'll try and figure out how should I do this, and it generally comes up with a pretty good color scale to just kind of scope things out. So what we're looking at here is Wattenberg. Here's all our well sticks. This is the well density within our polygon, and it's just coloring by that. And we can celebrate. That's pretty much all I had to go through. I mean, yeah, so if you guys have any questions, definitely let me know. And I can, maybe work through some of it here, or, if you have questions that I can answer later, hit me up on LinkedIn, or I think I have my email in this thing as well, so hit me up there too. Don't be shy.
That was awesome. I'm just open it up, and anybody has a question, just unmute yourself and fire away.
Hopefully it didn't go too fast, but it's tough when you've been in this stuff a long time to know what people know and don't know. And I think like some people I'm sure we have a lot of different experiences in the group. So
Donny, this is Ben Burke. Thank you for this. This was wonderful. I've become an R user. Python was my gateway drug into R. With SF, is the other ggplot and say USMap package functions and mapping ability?
You're kind of cutting in and out there, but I think the question was, is it compatible with ggplot2 and other plotting packages? I don't know. I think it probably is. I actually don't really use ggplot that much. ggplot2 is sort of like the standard, it's sort of become the standard plot package for R. And most things I think are written to be able to take advantage of it. I think it is. I tend to just very basically plot things up, and then I usually wind up dumping out shapefiles and looking at them in Spotfire or whatever.
Gotcha. Thank you.
Yeah.
Yeah, that was really cool. Thanks for walking through that.
Thanks.
I've used SF for a little while. The ST Simplify I didn't know was a thing, so that'll help save some time. Question for you: usually all of my scripts are just the base kind of setup here you got in the top left, and then a bunch of comments littered all over the place. Did you make your R Markdown in RStudio, and is that your like common place for if you're getting kind of complicated scripts to take notes of it, or how do you usually do that?
This is actually the first time I've created a Markdown, but it's really pretty easy to do. I did do it in RStudio.
Yeah. Okay.
let me open up what it looks like. There's not a whole lot to it. It's this RMD file. Basically what you do is I think you have to download the knitr package.
Okay.
Yeah, knitr. So you have to download that, and then I think it will give you this little menu here. And I really only use the one command. There's a ton you can do, I'm sure, but basically you just give it this like intro thing here. So it says like, you know, author, yada, yada, yada. And then you just type like what you want to do or your text. This is a different one than I think my final version here, but this would just be some text. And then if you want your code chunks, you put in here with 3 backticks and then curly braces. And then you tell it, this is our code. I want to call this section import shapefiles. There's a bunch of other options. I don't know if I have, this is not my final version, but there's a bunch of other options like evaluate, whether you want to hide the code, stuff like that. If you look up R Markdown, on Google, there's all sorts of real easy to understand examples. Like it's not hard to do. And then you just hit knit, and it like creates this HTML thing, and it generally looks pretty good from the get-go.
Yeah, thank you.
Yeah.
Donnie, do you do much subsurface work in R, or mainly mapping and stats and like a Spotfire add-on or drop end?
I do some. I mean, I guess what I try and do is things that I maybe can't do other places, or I guess I've been using R so long I kind of don't keep up with what's being updated in certain softwares and maybe do more than I should in R. But like I've been working on some stuff to try to like create pay flag curves using machine learning models, like feed a bunch of logs in, pick out sections of logs that correspond to like wells, and then try to create a model that will like figure out like a petrophysical model almost. I've done some stuff like that, just sort of, and pie in the sky type stuff. I have done some like trying to fit petrophysical models in here. So like bring in some logs, use like a standard petrophysical model, and just have it like solve for the best coefficients that fit things. So I do stuff like that, but not a ton of subsurface stuff really. Like if I need to make maps and make cross sections and stuff, I don't do that in here, I guess. That answers the question. I do a lot of like production stuff, like summing for production, forecasting it over groups. That's one of the most handy things I think about R is being able to do calculations over groups, loop them quickly. That's just sort of how I tend to think about things in my head now, about how you want to do stuff. So anyway, maybe rambling there. The best package I've actually found for that, though, if you need speed, is data.table. It's insanely fast. And the other one
bringing in log data. Have you ever tried? Can you plot like logs along laterals, or build pay flag curves, or flag anything like completions data or something along the maps as you're building this? Is that something you played with, or do you use it more for just the calculations?
I do tend to just use it for calculations. I tend to do my visualization in Spotfire. I think mainly just I don't know. I kind of started in Spotfire. That's what got me into R. And I just think it's faster. Like I don't like having to type, want my plot to be. I had Spotfire, so I guess I never took the time to really learn how to do it that well either. But I have done a lot of stuff like make a feature that represents like stages and then color them by like ISIP and stuff like that, which is kind of cool. Sometimes you can see like faults and stuff through paths, and I've done that kind of stuff, but it's usually in Spotfire.
Is there anything special or peculiar about trying to connect other data sets? So if you've got like completions or production data, and then you've loaded, say, the shapefile, trying to join those up so that you can visualize it or you get it together is one table for Spotfire?
Yeah, that's a good point. That's something I didn't really cover in here. What I use for that is merge. I'm trying to think if I have two things in here that I could merge together. I guess we could make two. Let's just do, we'll make like a little data frame that just has like operator and maybe API number in it. Let's see how we do this. So if you wanted to reference multiple columns, you would use the C function. So the C function just concatenates things into a vector. So I don't remember what the name of it. But I use the merge function, and let's see. Merge function is pretty much just like merge this thing with that thing by these other things. Do you want it to be inner, outer, yada, yada, yada. Well, there'd be our operator and our API number. And if, actually, let's make this. If you want to get rid of the geometry column, just turn it into a data frame. Use this st drop geometry. And that would just make us a little data frame with just API number and wells, and then you could merge them together with so merging op and wells by x. So this would be x, this would be y. And in this case, they're named the same thing. It'll try to find columns that are named the same thing, but you I don't like to rely on it to do that. So by.x and by.y is equal to API. And then if you want like a left join or a right join, you would just do all.x equals true or false. So if we want every value of this, regardless of whether you find something here, you would use all.x equals true and then all.y equals false. Should be able to run that and it'll merge them. And so that's how I tend to join things together. So yeah, if you had a well data table, you could use that.
Well, you could go the other way too and like join things into your shape files and then pass the shape file to like your GIS, your spatial GIS team, and suddenly they've got more data. Like you can get geology data or subsurface data or spacing data into their maps. Yeah,
so yeah, I do wind up doing that kind of thing fairly frequently. Yeah, that's a good point. One thing I think you do have to look out for is like if you're merging two different things, I think whatever the first one is what it becomes. So like it can merge a simple features collection and a data frame, but you know it has to decide if it's going to be one or the other when it comes out the other end. So in this case, we put the data frame first, so it's going to be a data frame. It'll still have our column with our geometry in there. It just sort of like doesn't know what it is anymore.
Gotcha.
Yeah. So Mark, what do you use simple features for? Oh, maybe you walked away.
I think he walked away for a minute.
Makes sense. I would walk away from me too.
He's got kids.
Yeah.
Can you speak any more about, like you mentioned it a little bit, I think it's a really cool work or concept for kind of as you think about in my head, I'm thinking about the rules of how you would think of either actual development or a valuation development plan that you would use for infill, like creating the number of sticks that you might value something on or want to plan development for. You made it sound like you've done a little bit of work on that side, more from the valuation side, but it seems like it should have an application to the operations side too.
What was the question? Just kind of an explanation of how it's done, or how
yeah. Well, so if you've got the gaps and you want to put in the extra wells, create the rest of the sticks to finish the development of some unit or some area, the kind of the logic that you've followed to try and do that, and how you, I don't know if you can speak a little bit about what it might have helped you think more clearly about as far as development or valuations around well spacing and development patterns.
the thing that it really helps with is being able to do it fast, because whenever you present like a acquisition opportunity to management, it's not just like, here's the value. It's like, here's the value in this scenario, here's the value in that scenario, here's the value in that scenario. And unless you're doing like, my spacing is 330, my spacing is 660, you've got to create another set of sticks, because your distances aren't multiples of each other, and you can't just like halve or double. So it helps with that. It helps if the one big thing it helped with is like, the way that I set it up was, you give it polygons and wells, and it would just make sticks within the polygons, within some length range that you give it. And it helps because you can take like, what if I pick up this block? Like, how does it change the length of the wells that I'm able to create, over a large position? Or what if I want to look at this company and that company? If you put them together, like, how would their lateral length distribution change, and how much would you get value that way? So this stuff that you can't really get unless you're doing a stick-based workflow. And I guess the other big one that I do a lot is, once you have the sticks, like in certain, like in the Permian, you've got like, you kind of have a development pattern that is sort of set. That the wells that are going to go in next kind of have to be in one spot, but maybe somebody owns little pieces. You can intersect those wells with a shapefile of acreage, and then kind of get like, okay, well, who are the working interest owners going to be in these wells? Even if I don't necessarily know like what their working interest is, you might be able to say, okay, here's this company's got like 50%, this one has like 25%. You can figure out maybe who's likely to operate based on stuff like that. So just things that you can't do with just like, here's my acreage and here's the number of acres I think is left, divide it out, get some well counts. You do more detailed analysis. Anybody else do spatial stuff in R?
It really reminds me of GeoPandas. It feels similar.
Yeah, I would guess that it is. That's the that's Python.
Yeah,
I assume. Yeah. Well, when somebody did mention, looking at logs and stuff like that in R, I do think that's one spot that Python is ahead of R. R doesn't seem to have a lot of like oil and gas specific packages. There is like an ARPS decline curve package. I don't think there's actually an LAS reader that I know about, at least not on CRAN. There might be some like GitHub versions out there. But yeah, sorry. I
saw somebody recently showing, doing a workflow in, I think they were using RStudio, but there's a way to connect RStudio to Jupyter Notebooks or Anaconda so that you can run Python and R within RStudio. And then you can use like Python to read an LES file, and then R to do the stats on the and some of your LES statistical work, and kind of seamlessly go back and forth and pass functions and variables back and forth. And there's definitely some cool power you can get there in RStudio.
Yeah, it's the reticulate package in RStudio is what allows you to write Python chunks in Markdown.
Huh, that's pretty cool. I have used, I was experimenting with some stuff at one point, and I used, I think, TensorFlow for R, which is just like a, it's basically what you describe. It's just like you have to get Python, and then it sort of just like sends everything to Python and does it and brings it back to R. There's another really good package that actually does that with C++, RCPP. And I've actually used that quite a bit for speed. Like if you've got like, I'm not very good at C++, if you have some like fairly simple function that for whatever reason does not run quickly in R, if you can figure out how to do it in C++, that can speed things up quite a bit. I think one of them I did was like date calculations. For whatever reason, it seems to take a long time for it to figure out like how many days are in a month. So I used like a C++ or RCPP to make like a how many days are in the month function that just runs really fast.
Has anybody done anything with the Shiny package, like making dashboards or interactive apps?
I know a guy who has, but I have not really done anything with Shiny.
Yeah, I haven't written anything either. But what Kurt just mentioned, we had, or I had like a Python script that did a workflow that was useful, and then, but you know, a lot of people on my team can't use the Python script, so he wrote the Shiny dashboard to like get all the inputs, basically like the user interface for the Python script, and then use the reticulate tool to type it right into the Python, and that seems to work really well.
That's pretty cool. We have one like we have a guy who's writing something in Shiny to like a pad planning tool, basically. Like we've built some models around like how do we think a pad will perform at a certain density, and he's sort of set up a tool that will use that model, and you can like kind of draw a pad in and it'll run the model, so you don't have to like go into R and do it all the time. So that's what I've seen it used for, and it works pretty well, but I've never done it.
Yeah, I don't know anything about it other than the like interface he made was pretty cool.
I've heard it's a little different to get used to because it's like interactive or reactive programming, which is not something I've ever done.
Yeah, has anybody, this is kind of going back to Python, but has anybody used a dash for Python before? I think it's kind of similar to that, but I've been learning that lately, but I don't know how it compares to Shiny.
What does it do?
It makes dashboards and interactive apps in Python. It's called Dash. It's by Plotly, the same developers that make the Plotly plotting package. I think it's similar. I think it's supposed to kind of be Shiny for Python, but I don't really know enough about Shiny to say.
All right, trying to read through the comments here to see if there's any questions I missed or could address.
I've been looking at them. I don't think there's. I think Ben had one question. Ben, did your questions get answered?
Yes.
So I think all that's mostly been conversations back and forth.
Cool.
Hey, Donnie, this is Zach with Roji. I've got a quick question for you.
Yes.
So right now in Spotfire, I'm developing a well spacing toolbox and have been looking to incorporate some of the embedded tear functionality and R functionality within Spotfire. Do you see this SF package as being the best package for something like that, or are there other packages that you like?
I do. So that's actually one of the reasons I started using this package, is because when you want to display shapes on a Spotfire map, they need to be in a format called WKB, well-known binary. It's basically just like a long binary string that like has known points where it's cut for coordinates. And this package has a real easy way to convert from simple features to WKB. And then, so basically that's what I have a lot of is like, that's sort of how my sticking program that I built and a lot of other stuff that I do works. Like I'll create my shapes like in a tear data function, and then I'll use SF to convert those shapes to WKB, and I'll kick that out to Spotfire, and then I'll have my, like it's basically like you imported a shape file in Spotfire. It'll come out that way. So that's one of the big reasons for me to use it. It's SP was what I was using before, and SF I think is faster than SP. Did I answer the question? I might have rambled there.
No, that was great. Thank you. I appreciate it.
One thing I have found is I don't know, maybe it's just the way our machines are set up at Ovintiv, but like I tend to use, there's a package called R&R, which lets you run Spotfire function or run functions locally. So like it basically goes from tear and then kicks it out to your local R and runs it and brings it back. And I've just had a lot better luck with like tear's always kind of like behind in terms of packages and stuff. And it tends to just work better when I do that. It does make things harder to deploy to other people. So that's kind of the trade-off.
Thanks, Donny. That's great.
Yeah, no problem. What was your name again?
I'm Zach with
Zach. Cool. Yeah, spacing calculations are tough. I think somebody was talking about that before.
I'm tempted to go down the rabbit hole of all the different ways it can be done. I really like the way you've approached it because I find I've seen lots of people do like counts per section or something, which creates all sorts of data artifacts. And I think that using the buffer the way you did is a kind of a nice concept that creates a well-level density term. I think spacing is constantly a fun one to find out all the wide range of ways that people can approach considering or quantifying spacing.
And I did that. Go ahead.
Oh, go for it. Well, I was going to say one thing I should show you. I want to show you something with buffers here that actually is useful for that, that it probably should cover. So it's not like that crazy. It's just like you can do different end caps and stuff. Like it's round this time, but like if you had a stick and you just wanted to draw like a square that sort of terminated at the ends of the stick, you can change the end cap style. I think it's flat. I don't remember exactly. Nope. Oh, there we go. Yeah, it gets crazy when you have weird shaped wells because it's like the well goes here and then it goes here. It works better for like a line. So you get this Pac-Man looking thing here, but like if you want to draw like square, you don't have to have it be a round buffer. It can be a square buffer is all I'm trying to say. Long way to say that. Sorry, somebody had a question?
No, it was just I was going to tell a funny story about a brute force spacing calculation where basically we went into a field and we looked for every bottom hole location and every surface hole location and then created all the laterals. And rather than trying to do it the way you did it, we basically made a function that compared every single lateral to every single bottom hole location in the entire field, and then just filtered out for the ones that were close enough to each other to worry about from a spacing standpoint, which we got it to work, and it involves some very tricky apply functionality, so definitely you're preaching to the choir on using apply versus looping, but it was probably not the easiest way to go about it.
Yeah, that's where ST intersects is like super useful. I don't know how it does it, but it's insanely fast.
The math of how you figure out if a point is contained by a polygon is one of the more elegant math functions I've seen in a long time.
Yeah, they're always fun to look into. I don't know how it's done, but there are other ones other than ST intersects. There's like ST contains properly. They all do the same stuff, but you know, if you want it to be inside, not intersecting, right? All sorts of weird things.
Well, Donny, thank you so much for putting this together. I think everybody has learned something. I certainly did. This was stellar. As we go on with everyone, there's more subjects that we're going to cover, and as other people have things that they'd like to see presented or want to present, please reach out to Mindy or I, and we'll try and get either your topic covered or get you involved. The conversation on the chat was awesome today. Thanks everybody for joining. Next week, we've got Matt Bowers to talk about some scraping algorithms using Python, which can be a real fun way to get away from some expensive services for data, or find ways to get data that might otherwise be inaccessible or too arduous to collect. I look forward to that talk, and I look forward to seeing you guys all then. And until then, feel free to shoot us emails and keep conversations going. And we'll see you guys next week.
See you guys. Yeah,
Thanks.
definitely reach out if you got any. If you have any questions about what I went through, feel free to reach out.
Yeah, and have a look at the Markdown notebook. I think I linked it at the beginning of the talk. It's in the LinkedIn as well as the email. It kind of goes through. You can see all the script that he put together.
I'll just stay on till the bitter end here in case there's any other things. But yeah, thanks for letting me do that. That's fun. I always like that kind of stuff.
Thanks a lot, Donnie. That was a great job.
Thanks.
Thanks, Tommy. That's great.
You're welcome. Thanks for listening.